So today let me discuss this bending moment problem. So now in this problem we will learn how to sketch the bending moment diagram and also how to find the critical points that are related with the bending moment diagram. so uh, so now let's see. I think in this problem, as you can see here, I have described. Here I have given the description of the problem, because like most of the time, like what I see in solving this problem is students are expecting the diagram all the time. They expect the diagram like this, right? So basically this is the diagram that I have sketched. So don't expect this diagram every time. Okay, so now let's see whether you can understand the diagram. So now here it is very clearly said that length of the beam is defined by AE as 20 meters. AE as 20 meters. 6, 10, 4, that means 20. Okay, so uniformly distributed load of 80 kilonewtons per meter was placed from A to B such that AB equals 6. Okay, so here we can see from A, this is the point A, from A to B, uniformly distributed load of having like that load, there is a load of 80 kilonewtons in every meter length, 80 kilonewtons. So that uniformly distributed load is applied from A to B, which is 6 meters in length. And then while the beam portion from B to C is loaded with a trapezoidal load structure such that BC equals 10, where the load intensities, be very careful guys, this is something, it's not complicated, but this is something that you have to understand very carefully. While the beam portion B to C is loaded with a trapezoidal load structure such that BC equals 10. Okay, so what is that BC equals 10? So this is the B, this is the point B, and this is the point C, right? BC equals 10. I mean this length is 10, and it's a trapezoidal load. Now you can see this is like this is in the format of the trapezoidal load, as you can see. Okay, so now it says, now the important point is the load intensity. That is the most important point, because now in this problem it says the load intensity such that at point B we have 80 kilonewtons per meter and at point C we have 200 kilonewtons per meter. Okay, that means that here we have 80 kilonewtons per meter, which is continued from the previous part, and at here we have the load intensity of 200 kilonewtons per meter. So that is how simply this this trapezoidal format is formed. I hope you can understand that, right? And that's it. And then it says a point load of 40 kilonewtons is placed at the point D such that CD equals 2 meters. Okay, so this is point C, this is point D now, right? As you can see, this is A, and then B, then CD. Okay, such that when CD equals to 2 meters, there is a vertical load of 40 kilonewtons. That vertical load of 40 kilonewton is placed, which is acting downwards, right? So now here a point load of 40 kilonewton is placed at the point is such that CD equals this much acting vertically downwards. Okay, so that is also done, right? So what is the other part? Two non-fixed supportive connections are placed at the two ends of the beam. Okay, so now in this beam there are two ends, end A and end B. Okay, so non-fixed, that means these ends are not actually fixed, right? So these ends are not fixed, so some supporters, that is what it says, two non-fixed supportive connections, that means some sort of a support, right? So two supports are placed at the two ends. So that is simply the diagram. So that is the first thing that you need to understand. So now you know the diagram, everything is clear now. So now what you have to do is, I think what it says, so what the problem says is sketch the bending moment and the shear force diagram with all necessary calculations according to the described loading condition. Means because there are certain parts of this question. Today I will be discussing only this part. So later I will discuss the rest of the questions. So and here the lettering, you can see the lettering will be started from the left side. That means how to say that these A, B, C, D, these lettering of the diagram will be starting from the left side. Now this is the left side. Okay, so now you can understand the problem, because I am giving the fullest fundamental explanation. So you can't say that you cannot understand, because that's my target, right? So now you can very clearly understand the problem. So now guys, just tell me, now what is the basement of this problem? So there is a beam having length of 20 meters, and there are certain portions such that in A to B there is a certain portion, then from B to C there is another portion, then C to D there is a portion where 40 kilonewton load is acting, and then at the extreme left and right ends A and E, two supports are placed. That means in order to support the beam, right? And this is not fixed, right? Some support. Okay, and this trapezoidal load. So now let's see how to solve this. So the very first thing that you have to focus is the vertical equilibrium. Okay, so in this problem now you can consider the vertical equilibrium. That means you can say because now this should be at a balanced position, right? Right, so the entire system should get balanced, as you can see. So now you can say because of the support at RA, there is a supportive force that is acting vertically upwards, and also here also because of this support at RE, there is a reaction that is acting vertically upwards, right? So here we have two reactions that are acting vertically upwards, and these two reactions are used to balance the total downward forces. Easy, right? Total downward forces. So that means RA plus RE, total vertical forces, equal to total downward forces. So what is the first downward force? 80 kilonewtons in meter, and our length is 6 meters, so that means 80 into 6. Okay, so that is done. And the next portion, guys, here you have to consider this area, right? So here you have to consider this area, because the area of this trapezoidal form, right? So the net area, the total area of this trapezoidal format will give you the total force or the total load, because this is the force balancing. Okay, so what is that? So very simple, half, that is how the formula comes, half into this basement, which is 10, into the sum of parallel sides. I think that is grade 6. Half 10 into sum of parallel side, which is 80 plus 200. Okay, plus this vertical force. What is this vertical force? 40 kilonewtons. So solve this. So now you can get a kind of an equation such that RA plus RE equals 1920. That is equation number 1. They're very simple. Okay, you cannot say that you can't understand this. It's very simple. Okay, if you cannot understand the simple basics, I don't think that you should select engineering. Nothing much to worry, simple basics. Okay, so, and the next thing, so what is the next thing that so now you need to evaluate these RA and RE. Okay, but you can't do that by using one equation, so you need at least another equation. So now you can consider the moment at whatever the point, because now if this system is balanced, right? So if this system is balanced, you cannot have net moment at any point. So but the fact is, you have to consider the point where you can eliminate one unknown part, because like if you are going to consider the moment at somewhere else, again these two variables will come, so you cannot find, because these are the simple basics that most of the students are missing at the exam. because of the confusion. So you can get the moment at point E. You can get the moment at point E in what direction? You can get the moment in clockwise direction. Okay, so clockwise way. So I will just okay, I will open. As you can see, I will just get the pen. So now this is the point that I am going to consider to get the moments. Okay, this is the point that I am going to consider to get the moment. So now I am going to get the moments around this point, right, because of these forces. Okay, so because of this upward force Re, the moment that is effecting on this point would be, that is the clockwise direction, right, where the clock points are moving, and the moment around this point because of these vertical loads would be in this direction, right? So that is the basic. Okay, so I will come to that point when I'm going to teach you that. Okay, so one by one I can discuss that. So now basically guys, this is the particular point that we are going to consider to get the moment. Okay, so now I am going to consider moment at E, that means the moment at here. So what would be the first moment? What would be the first moment that would come? This force Ra multiplied by this distance, which is 20, Ra into 20. Okay, right, see, Ra into 20, and right, so that you can understand this force multiplied by this length. Very, very easy. Okay, so just undo. Now how to get the moment due to this uniformly distributed load? Okay, right, so now this part is okay. So now let's see how you are getting this part, this 80 into 16 into 12. Now let's see how to get that. Okay, so now you can see here, starting from this end and up to here, right, starting from this end to there, you have that uniformly distributed load. Okay, so what is the length of this span? What is this length? That is 16. Okay, right, so now it's very easy. So now if you are going to consider this length 80 kilonewtons in 1 meter and the total length is 16, so what is the total weight, what is the resultant weight that is acting from here to here? So that is 80 into 16. Okay, that you know, so that is 80 into 16. So very easy. And what is the center point where this resultant load is acting? You can consider this as a simple length or simple beam. So the centroidal force would act at the mid, that means the mid of this section. You have to consider the mid of this section. So what is the mid of that section? That is somewhere here. That is somewhere here, right? So that is the mid. So that is the mid. So at this mid, I will again undo. Okay, so now in this section, if you are going to consider this section, so the mid portion will give the total amount, so which is 80 into this length, which is 16. Okay, so this resultant load is generating a moment at here. So what would be the direction? If this is the point we are going to consider and this is the load, so it would go in this direction, right, anti-clockwise direction. So what is the length? Here to here we have 4 and here to here we have we have how much? This is 16. So here to here we have 8. Is that clear? Here to here 4 as given in the diagram, and here to here 8. So the total will be 12. So now you are getting 80 into 16 into 12. So now here what is this 12? So this 12 is the distance from the center point of the resultant load and the point we are going to consider for the moment. Is that clear? Yes. So now the next part. These are not complex, guys, because you need to study from the basics. So now after that, so now the thing that you have to focus is because now we already considered this RA guy, and also we now these are the things that we have considered. So we already considered this RA reaction guy, and this pan, right? We consider this pan. So now the remaining part, there are two remaining parts, like this one and this one. So these two are the remaining parts. Okay guys, done. That's okay, right? So now these two are the remaining parts. So it's very easy. So now just consider this triangle. So if you are going to consider this triangle, if you want to find the load, okay, so if you want to find the load, you need to consider, like if you want to find the resultant load because of this section, now you need to consider the area of this section, the area. So what is the area of this section? Half into half multiplied by this base into height. Okay, so now how can you find this how can you find this height? How can you find this height? Because you know this total length, this total length is 200, and you know this portion is 80. So what is this height? What is this height? So it would be 120. Here it is here it's a point. So now you know half into base into height. So what is the base? That is 10. So that is how you are getting this one, half into base 10 into height. So height is 120 as I have mentioned over here. Okay, so now that is the total load. That's the total load. So now the next thing okay, so now if you are going to consider this guy, can you please tell me, right, in this section or in this part, what would be the center point where the resultant load is acting on this triangle? So guys, just keep that in mind. Okay, so in that case you need to know the centroid of the triangle. Okay, so that is 1/3 of the height side. Now this is the height side, because now here you have the height, right? Here the non-height side, because here there is no height. So the center of gravity will act 1/3 from the height side. Now because this is the height side, no, this is the length. So if you just approximately divide this into say 3 portions, 1, 2 and 3, so the center of gravity would act 1/3 from the height side. So that means this is the place where the center of gravity will act. So now what is this length? What would be this length? So that is 10 divided by 3. So that is this length. And what is this length? 4. Okay, so now what would be that distance? 4 plus 10 divided by 3. Very basics. And the rest part is easy, 40 into 2, because and just consider the moment, because of this guy is also going in anti-clockwise direction, so like this. So that is why here you get negative. And the same case for this guy also, I think okay, I'll just erase this. If you are going to consider this guy, that is 40, And what is the length from here to there? From here to there it is 4, here to here, because you need to identify the distances. Here to here it is 2, that means this length would be 2. So minus 40 into 2 acting here. So minus 40 into 2. So that means now you have two forces, you have two equations, this one and this one. So from the moment equation you can evaluate Ra, because you got the moment at the point E. Then by considering the system of the other equation systems, you can evaluate what is Re, because from this one you can evaluate what is Ra, and that value you can put here, and you can find the reaction forces. And also you can use the simulation softwares, but guys, whatever simulation software or not, you should know the basics, and if you don't understand the basics, it's pointless. So that is why I took this much of time to teach you these very basics, right? Very basics, right? This is a diagram, the force structure, everything would be given. The first thing that you need to evaluate is how to find these forces, this one and this one. Okay, so now you know how to find these stuff, because I have explained you starting from the fundamental things. Okay, so now we will discuss how to sketch the shear force diagram. So now basically, before sketching the shear force diagram, before sketching the shear force and bending moment diagram, there are certain things that we have to consider, because it's because it contains certain steps, certain logical procedure. So now let's see how we can calculate the shear force, how we can calculate the shear forces, and then the bending moments, and then sketch the bending moment and shear force diagram. Okay, so now as we know, this is our diagram. Okay, so now here we are going to do some sectioning, right? So now I will teach you how to do this sectioning thing. Okay, so that means based upon the different types of forces and different types of force distributions, how to say that, based upon the different types of forces that are acting on this beam. So as you know that basically this is part A, B and C, D and then E, because you know that is how we name this beam. So now you can identify there are certain differences based upon the forces which are acting on this beam. So let me tell you that, right? From A to B you can observe there is a distribution of forces like this. Okay, from A to B, right? Because it's something like, you know, different stages or like different chapters. From A to B we have such a kind of a different chapter, and then you can see again from, you know, B to C, that's a different chapter. So what do you mean by this different chapter? Means like different type of force distribution, right? So like this, up to C there's a different chapter. Then from C to D also there's a different chapter. Why? Because like there is a load component which is 40 kilonewton, that is acting on the beam, so it's a different chapter. And from D to E also there's a different chapter. Why different chapter? Because this RE coming, so it's a different chapter. So like that you can do certain sectioning, right? This one section, another section, and the final section. Okay, so now we are going to consider the first section, the very first section. Okay, so now we are going to consider the very first section, and now we are going to find the shear force on that particular section. Okay, so now basically like shear force is like by doing this kind of sectioning, right? So you can see here I have considered like shear force for the section AB, for the section BC, and see for the section C. So like that I have categorized into certain sections and I have evaluated the shear force on those particular sections. So now let's see how to do that. So now this is our first section. I say this by section AB, and there is a way that how we are going to introduce this section. So now we define this section as section AB, okay, but how we are going to define this? We say that 0 greater than or equals x and less than 6. Guys, be very careful when you are going to define the section. 0 greater than or equals x but less than 6. It is not less than or equal, okay, it is less than 6. That means you are not going to consider the whole length, no. So you are just going to break this section just few units before the end of the section. How should I sketch that? Now this is the total section, which is 6 meters, and you are going to break this section just few units before that. Understand? So so that distance is actually x, okay, right? Just few distance away from this point, right? Up to from this point up to here it is 6, and you are going to just break it before some little little distance, something like delta x, let's say like that. So now we are going to find the shear force over there. So now basically what is the shear force means? Shear force is how the force is distributed, okay, right? The force structure, the structure of the forces. So now let's see how we can basically evaluate that, okay. So now I will teach you how to do that. So now just say this is our section. I told you that, right? This is our section. So now I told you to consider 0 greater than equals x less than 6. So that is how I told you, okay. And if you are going to consider this section, there is a reaction force. I think I will use a different color. Now there is a reaction force RA that is acting here, okay, and there is a uniformly distributed load like this, okay, uniformly distributed load like this, and those are the only forces so that are acting over here in this section. So section AB, okay, right, that's a section AB. So now also I think I want to mention something very specifically about the direction, because majority of the students are mixing up this direction. So now I will teach you that. Guys, just consider this beam, okay, and this is the left hand side and this is the right hand side of the beam, okay. Be careful, very important, very very important. So now just think that you are going to apply a force on here like this. So just say that from this side you are going to keep your finger and you are going to hold this side. By placing your finger you are going to hold this side, okay, and because of the force that is applied at this left end, you can observe that this rod will tend to rotate in this direction, or in other side left side will go up, okay. this is the beam. Here you are going to apply a force, and this is the left side, and because of the force that you are going to apply on the left side, so this will go up, or in other words you can say there is a moment like this. So it is even simple if you say left side will go up. Very easy, right? So if left side going up, we call it is positive shear force. Got it or not? Like left side go up, like left side goes up, it's positive shear force. So now just consider this section, guys. Now if you are going to consider the shear force, because of this force Ra, this left side will go up, right? Just imagine you are going to place your finger here, right? So you are going to place your finger, so because of this force this will go up. So this Ra causes positive shear, that is the direction. There are certain other ways, and this is how I teach. So this Ra, okay, and then you can see there's a uniformly distributed load. So what is the value of that uniformly distributed load? I think that is how much is 80. So minus, but why minus? Because the resultant force causes, like the resultant force that is towards the downside, right? So that is downwards. So because guys, now what is this distance? X, right? It is not 6, it is not 6, it is X, because I told you it's not X, actually it is little bit before the length 6, so it is X. So what is the total force now? So what is the resultant force? I told you it is 80 kilonewtons per meter load, and it is applied for a length of X, 80 kilonewtons per meter, and it is applied for a distance of X. Okay, so you got it? That's the point. So the resultant force is 80x. It will act at the mid, that's okay, that is something else. Now if you are going to consider this section X, it will act at the mid. So now what is that midpoint? It is X by 2, because the center of gravity of the section whose length is X would be X by 2. Okay, but anyhow, so what is that total load? 80 multiplied by 2, that means 80x, and you know that the value of that reaction. So what is Ra? I think Ra is 992, that we already evaluated. So shear force is 992. Guys, carefully see this, 992 minus 80x. Now that is the shear force, the general shear force equation. You can say this is the general shear force equation, not for the whole system, only for section AB, right? So that is how it happens, only for section AB. Now see, you can shear force for the section AB, Ra minus 80x, Ra minus 80x equals 992 minus 80x. So be very careful. Okay, so because these are actually, guys, simple basics, but I want to teach you from the very fundamental thing, right? From the very fundamental thing, right? Otherwise you people will not understand these basics. So now uh, now you can see the section AB, this force is there and the spam force is acting up to a length of x, right? Because like we have separated the section, right? We have separated that particular section as I earlier mentioned. See, so like here, okay, see we have just cut this section. So that is how we are going to evaluate the shear force. Okay, right. So now let's see the next part. Now as you can now understand the fundamentals, now I can go for the future things. So now you know how to obtain this part. That's okay. This part also okay, because now this is the general equation. So if you could not obtain this general equation, right, you are not getting the full marks. So now what is the next thing? The next thing is, now you know the range, that means the limits, because this starts from x greater or equals x and less than 6. So now the next thing is very easy. You know the general equation, so find the value of shear force at these two limits. So what are the limits? This is one limit and this is the other limit. In this general equation, put x equals 0. So what is the value you would be getting? This is 992. And then put x equals 6. Guys, that's the way, guys, okay? Then put x equals 6. That means 992 minus 8 into 6 is 480. Right? So what's the answer? 512. So that is the answer. So that is how you are going to evaluate the shear force equation and the shear forces for the particular section. Okay guys, this is a very big journey, but I want to explain you each and every step in detail. Okay, so now we are going to move to the next part. I think now there is no any sort of a doubt in the shear force values. Okay, I think it's clear. So now our next target is to understand this guy, the same thing for the bending moment thing, right? So that is also easy, it's not hard. So now let's see how we can evaluate that. Okay, so don't need this part. Okay. Right, so now again I will teach you from the very basics. Now the next part is for the bending moment. Again consider this section. Right, so now you know the section already. 992. Okay, and this, that's a weight span, the uniformly distributed load that is acting, and this is the end of the section. Okay, so this is 80 into x, you can say 80x. So now let's see how to sketch the bending moment for the section AB. Okay, bending moment for the section AB. Okay, So now guys, I will again say, just because of the force that you are going to apply at the left end, because of the force that you are going to apply on the left hand, by considering the right side as the pivot point, if left side goes up, guys, that is what you call positive bending moment. Understand? So now, right, so because of this force, this vertical reaction force, when you're going to consider this as the pivot end, right, you can say this is something like, pivot end, something like that. So this is pivot end fix. So now this will give the moment like this, right? This side will go up like this, left side will go up, so that is, it is positive bending moment, right? So it is the positive bending moment, because otherwise you don't know how it is defined as positive. So that would be 992 multiplied by the distance. Guys, what is the distance? It is x. So this distance is x, so 992x. And now the next thing, what is the next load? 80x, right? So load of 80 kilonewtons per meter load is applied for a distance of x meters. So what is the total? 80x, right? So now the next load is 80x, so that 80x load will act at the mid, right? Because guys, it is the center of gravity. So because of that 80x load, the left side will not go up. That's natural, right? Because guys, whatever the load, this side or that side or that side or that side or this, or whatever the load, guys, you just consider your extreme right side, this side, as the pivot point, right? I will sketch that again. You just consider this side as your pivot point, right? So now because of this 80x force, okay, so this left side will go downwards, not up. So like that, because of this 80x, now you know the basics, so it is negative bending moment. So that means minus 80x multiplied by, because this is just the force part, okay, times the distance. Very careful, guys. So what is the pivot point in this section? What is the pivot point here? Because this is how I sketch the pivot point of it. Okay, so if it's not clear, I will sketch again. I will sketch it again. Now this is the pivot point, okay. Now this is the pivot point. So now this is that what you call as this 80x guy, right? So the total length is x. So what is this? Where is the center of gravity? Is here. What is this distance? X by 2. So what is the perpendicular distance from this load to the pivot point? X by 2, guys. So what is that distance? Multiply. Oh, guys, careful. This is also x, but this is a multiply. This is a multiplying symbol. Multiplied by x by 2, because that is the perpendicular distance. Okay, right. So it's very easy. The bending moment for the section AB is 992x minus 80x squared by 2. I think now you know how to get this part. See guys, RA x minus 80x squared by 2, 992 minus 40x squared, because 80 divided by 2 is 40. Very fundamental, very fundamental. It's very easy, right? It's not hard. Okay, it's very easy. So now guys, I'm getting this much of efforts to give you the best service, because different students are having different level of understanding capability. So just watching 5 minute 6 minute video, sometimes you will never understand the basics. because even you at the undergraduate level, I know certain students are there, they cannot even understand the simple basics. So that is why I thought to teach like this. So this is that section. Now you know how to get up to that part. So then you know this section is valid for a certain range. That means basically for two limits, 0 and 6. So then to this general equation, right, to this general equation, first put x equals 0 and find the value. When x equals, so when you are going to put x equals 0, 0 bending moment, and when you are going to put x equals 6, right, so when you are going to put x equals 6, this is the bending moment that you are getting, 4512. So guys, to this section there are 2 shear force values and 2 bending moment values. I think the analyzation for section AB is now completed. Right, so now let's move to the next part. So now we are going to consider the second section. Okay, so now the second section means we are going to move on to the second chapter, right? So that doesn't mean we are completely going to forget the first chapter, including the first chapter. That means now, as we know, this is the first chapter that we solved, where this region is defined as x greater or equals 0 and less than 6. So now we are going to extend our chapter up to here. So now we have new x, because now the x at here is not the same x as in before. So now, like when you are going to consider the original diagram, like here, now we can see this portion, right? Like this portion is very special. I think it's better to get it from here. Okay, so now you know this portion is very much special, because now this is the end. Now this is the end of the trapezoidal load, right? So this is the end of the trapezoidal load. So now we are going to consider the second section like this. That means we are going to break it from here, right? Some little few distance, say delta x. So we are going to break some delta x away from this point, because this point is some sort of a turning point where it is the end of the trapezoidal load. So now our next section is this. That means section BC. Now you can also say AC, but you better call it BC. That doesn't mean you are going to neglect this part. You are including that part also, but you are going to define this section by BC. Okay, so what is the speciality? Now that means when you are going to consider this section BC, so be very careful on how you are going to name it, right? So the section BC you are going to name like this: x greater or equal 6 and less than 16, because the reason this is 6 and this is 10, so the total length would be 16. Okay, so you are going to consider, you are going to break this part some few distance away. So now this is the new section, that what you call as x. So this is the new section x. I think now you can understand the section. So the way that we denote the section is like this: greater equals 6 and less than 16. So only up to here, right? I think so now you can understand the section. So now we can quickly move to the shear force and bending moment, because this is also easy. This is nothing harder in here. Actually there is nothing much harder, right? So same procedure. So now I don't think that I need to explain everything in detail, because now you can understand the very fundamental. So now you can do this. So the next section, now here you can see this zigzag mark, like this mark indicates that I have separated the section. Okay, so now the problem is there are certain things that you have to consider, okay, because here you can see some special notification called phi. Did you see this guy, phi or phi or whatever? So just call this variable, right? So now the reason why I have introduced that part is that basically the reason for that is now you know that now I think I will undo this. So now you know that this part is only 200, right? This part is 200 kilonewtons per meter. It's only this part, okay? It's only this part. But if you are going to break it from here, so then what is the value of this load intensity? So that's a doubt, right? So we don't know what is that load intensity, right? So in that trapezoidal load format, right, when it reaches the entire 16 meter length only, it is 200. So now we are going to break this, so we don't know that. So but we know this length, because we know this length, I mean this guy, that is 80, right? I mean this portion. So nothing much to worry about that. So now we have to focus on what would be this. So we don't know that, so that is why we are going to say that this section is 5. So I hope you can understand. Now see, this part is 5, right? So this part is 5, right? Okay, right. So this part is 5, so that is okay. So now let's see how to consider the shear force diagram. You know that this RA, no worries, it's positive upwards, minus 80x. Now what is that minus 80x? This 80 kilonewtons per meter span, it continues up to here, right? So no doubt it just continues up to here. So no worries, it is acting downwards because it tends this beam to move downwards, so it is 80x. So no worries, no doubt, no problem. Okay, there's no problem. So now you have to worry about this guy, this member, okay, this member, right? So now you need to calculate the area. So what is the area? Half into base into height. Half, what is this? Base. So how you are going to find the base? This distance is x. You know this distance is 6. So what is this base? What is this base? So that is x minus 6, right? This base part, the part I am going to talk about, this part. So half into base into height. So height is phi, this height. I am talking about this height, this guy, right? Okay, so half into base into height. So now the problem is, it's okay to keep x minus 6, but you can't have another variable. Okay, so you need to find what is this 5 actually. You need to find this value. So for that we are going to use the ratio. Now you know this is 80, this length, but we are going to consider only this triangle, right? So only this triangle. So you know this length, that is 200 minus 80, which is 120. So now you are going to consider the ratio theorem. Okay, so ratio theorem is so now you know this. According to second case, you are going to break it from here. So now, so this would be the next trapezoidal. Our original trapezoidal format is this. So the ratio of the original height, now this is the original height. What is the original height? 120. How? 200 minus 80. So the ratio of original height to the original width. What is the original width? It is this. The ratio of original height to the original width equals the next sectional height. What is the next sectional height? Phi. To that corresponds, so phi divided by x minus 6. So that is how that part comes. So then you can find what is the value of phi. Is that clear? So I hope you can. Negative. Now here you can observe negative. The reason why, because it is negative shear, right? So it's negative shear. Okay, is that clear? It's negative shear. So Ra minus 80x minus half into x minus 5 into x minus 6 into 5. So you can actually simplify that, guys. I think this 5 is 12 into x minus 6. That means half into 12 means 6. That means this is the general equation. So what is this? What is this? 992 minus 80x minus 6 times x minus 6 square. What is this? This is the general equation for what? For shear force. General equation for shear force only for section BC. Only for section BC. So just put the limit, because now you have two limits, as indicated from here. It got two limits, 6 and 16. So just put x equals 6 and find the particular shear force value. Then put x equals 16 and get the other respected shear force value. And be very careful about the direction. And that's it. And now we would be moving towards the next part, the bending moment part. Guys, that is also very, very easy. It's nothing hard, so nothing much to worry about that. So now it is the second part, right? So now you have to consider the what you call the bending moment part, so where the moment comes to play, right? So now again you have to consider the diagram. I think I will consider this guy again, like this diagram, because this diagram is very much important. So right, so now let's just see. Bending moment also is easy, it's not hard. So the bending moment due to this Ra, that is positive, right? So acting upwards, so no doubt. Now see, guys, because of this reaction, that is same as, that is you can similarly derive from the previous step. That is a way of checking actually. Okay, Ra, this Ra, so it is like this tends the left side to move upwards, so that means definitely it is Ra into this length. So what is this length? X, right? Ra into X. See, guys, now it is Ra into X. I think so that part is okay. And 80x x by 2. Okay, let's see how that guy comes. So it's very easy. This is 80 kilonewtons per meter, that uniform distributed load, and it continues up to here, right? This continues up to here, right? So the total load is 80 multiplied by x. Total load is 80 multiplied by x. But what is the center point? X by 2. So this is the center point. But this is the center point, okay? Center point. Because now actually in bending moment, you are going to find the moment due to the forces which is actually the moment. Okay, I will tell you that it's a very important part. Let me just tell you what is actually bending moment. Like what you are going to find in bending moment is like you are going to find the moment due to these forces on this section, right? The moments due to these forces on this section, you are going to find the moment of the, I mean, like in the earlier way. So like in the earlier manner, I think you can remember you in considering when finding the reaction values, you found the moment at the point E. So like that, so like the way you found the moment at the point E, so here actually you are going to find the moment on this section because of these forces, right? So this is 80 into x. So now this is the section, okay? So what is this distance? X by 2. Why? Because this is the center of gravity. If it is not clear, I will round up, like I will just go back again. Right, now here we have the span. So here we have the span, and here the center of gravity, right? The center of gravity here, okay, the center of gravity. And then you are going to find the moment that is affected on this section, right? Moment that is affected on this section. So this distance is x divided by 2. So what would be the total impact for the bending moment? 80 into x by 2. Is that clear? Right. So now the next impact is because of the trapezoidal load. Actually it's not trapezoidal actually. So now, because now we separated the trapezoid here, because here we have separated the trapezoid. As you can see, if I am going to consider it like this only, it will be a trapezoid, right? So if you are going to consider like this, it's a trapezoid, like this, okay? But you have separately taken the uniformly distributed part, and now here what you actually consider is just the triangle, okay? Just the triangle. So that means you know the area of this triangle. What is the area of this triangle? Half into base into height into what is the distance to the center of gravity? 1/3 from the height side. So this is the height side. So if you are going to consider this triangle, this is the height side, right? This is the height side. So it's 1/3 of this length. That means somewhere approximately here, because the center of gravity of this triangle acts here. That gives the area. That means that area gives the resultant force, which is half into base. What is the base? X minus 6 into this height 5. What is that height? 12 into x minus 6. That means 6 times x minus 6 squared, right? So that is the total force. So multiplied by this distance, right? Because this is the force and this is the distance. I think if it is not clear, I can sketch it again. Right? Okay, so I will sketch it again if it's not clear. Okay. Right. So the center of gravity is somewhere here, and you know this distance. What is this distance actually? It is 1/3 of this length, 1/3 of this base. So what is this base? X minus 6. So 1/3 of that is 3. So that is how here in the bending moment equation that x minus 6 divided by 3 part comes. So now this is the general equation. So now you know the general equation for that. So now it's very easy for me to teach you, right? So now you know that part. So now you know how this guy comes. RA into x, 80x into x by 2, half into base into that height, this part. What is this part? What is this part, guys? The area of the triangle, half into base into height. And this is the distance from the force to the section or to the point you are going to consider the moment, which is the distance between the force, the perpendicular distance between the force and that point, x minus 6 by 3, like this, right? Because now this is the section you are going to consider for the moment. So now you have obtained the general equation. So if you solve that carefully, it would be 992x minus 40x squared minus twice x minus 6 to the power 3. So carefully put the values, very carefully put the values. It's like very carefully, guys, put the values. So if you carefully put the values, because you know the limit, so when you put x equals 6, you will be getting bending moment 4512, and when you put x equals 16, the next limit, you will be getting the bending moment like this, right? So now you know each and every part. Okay, so now bending moment clear and shear force clear. Okay, so now that part is clear. So now consider the section, the next guy, the section Z. Okay, so now we are moving on to the next section. So the next section that we have is CD, the section CD. So now we will see why we consider CD as a section. So now, as you know, we have already analyzed the previous sections, such as A to B we have analyzed, then B to C, and then C to D. So this section C to D is our next section. Okay, so now basically here what we are going to do is, like, we are going to consider distance x, which is measured from the extreme left up to some distance that is some little bit before the ending point. No, actually this is the ending point. Okay, so actually this is the ending point, but I told you we are going to consider the section some little distance. So you can say that little distance as say delta x. Okay, say some delta x. Okay, so that much before the ending point, right? So the reason to consider the section CD as a new section means now here we are getting some new member. I mean, like, here we are getting some new character, because I told you, like, we are going to separate the sections based upon different chapters. A to B different chapter, B to C different chapter, and also you should know why we have to consider BC as a different chapter. Why? So because the reason, we have a different type of load in there. So like that in CD also we have a different chapter because of this new guy, 40 kilonewton. I hope now you can understand about the section. Okay, so now basically in this bending moment case, what we are actually going to do is that, now I already told you the section, so we are going to break the section at here, right? So you can put some breaking symbol. So now we are going to break the section. So right, so from this extreme end, so from this extreme end A to this broken section, we have x. So now what we are going to do means, we are going to find the effect on this section because of these forces, because as we know, because of these forces we have this reaction RA and these distributed load, right? So because of these loads there is a torque, or there is a moment, right? So we are going to calculate the effect of these moments on this section, right? So we are going to find the effect on this point, which is x distance measured from the left end. This is the left end because of these forces. So simply that is the scenario. Okay, so now we can focus, because now already you have a kind of an idea based upon how we calculated that for previous scenario. So now let's see how this comes. So now for the first thing is the shear force, right? So now let's see how the shear force comes. So just look at the formula, right? So according to the formula, it is the reaction and then the span and then the triangular load, right? Okay, so let me explain that again. So okay, so I will just undo everything, right? Okay, right. So now you know, now when you are going to consider this loading structure, there are certain ways. So either you can consider this as it is highlighted. So either you can consider this rectangular section plus this trapezoidal section, understand? Either this rectangular portion plus this the trapezoidal format, that is one part. And right, so now here according to this calculation, here actually what I have done is I have considered this entire rectangular portion up to the end. That is also possible, right? Because you can consider like that, because I have considered this entire rectangular portion. Very easy. This length we know it is 80, but in a different unit. Okay, this is 80 and this distance we know that is 16. Okay, so that is how I have considered, plus I mean this whole rectangular plus this triangle. That is how I have considered in the calculation, because that is easy, because this base you can, this base you can calculate. This base, what is this base? 10. So height also because this is 200 and up to here it's 80, so the balance is 120, right? So that is how I have considered in the calculation. Okay, so now we have our section, now this is the end A, and we have our section D, right? Because now D is the ultimate section, right? So we have our section D for like 20 meters. Now see, here to here 6 and then 10 and then this is 2, that means 18. It's 18. Okay, because like the ultimate length of this section is see, you can see in the problem, you can see that okay, I will again get that for you to show that clearly. So now here to here it is 6, here to here it is 10, that means 16, and with this 2 it is 18, right? So our ultimate section is 18, right? It's 18, right? So but we are going to break this at some particular section like this, and we are going to say the distance measured from this end to this section is x. So we are going to find the moment that is affected on this point, which is x meters away, due to these forces. So that's simply as that. So now it's very easy. Now we can see that. So now you can see here we have this force, the reaction force Ra. This reaction force Ra is there, so that is generating a moment. So what is the direction? It is positive, guys. Why? Because the left side going up, that means it's positive. That means this Ra times this distance up to this section. So I told you this is the section, so Ra multiplied by the length up to the section, that is x. It's very easy, right? And okay, now how to consider the other part. Then after we have that rectangular load, this rectangular load, that's also very easy. So what is the total load of the rectangular section? 80 multiplied by this length, 80 multiplied by 16. And now what is the, where is the center of gravity? That is at mid. We'll use a different color. So that is at mid, at here, center of gravity at mid. And you know this length is 16, so the center of gravity, I mean the distance to the center of gravity from the left end is how much? So that is 8. Distance to this center of gravity from the left end is 8. So this distance is x, and so what would be this one? So what would be this one? It is x minus 8. So x minus 8 is the distance from the center of gravity of the rectangular load and the point we are going to consider the moment. So now you can see that is how they have considered. See the section CD, right? So that's easy. That's the moment actually. I think first I have started from the bending moment, which is the harder one. Okay, doesn't matter. See, you can see guys, okay, doesn't matter. So you can see it is very easy. Okay, first we will consider the bending moment guy, right? Because that is the harder part. The reaction times the distance, very easy. So then negative, because like it causes the left side to go down. So 80 into 16, 80, 16 into x minus 8. So done. And the next thing, so what is the next thing? In next thing guys, we have to consider the entire triangular load, right? So it's natural, right? So you have to consider this entire triangular load. I think I'll use a different color. So you have to consider the entire triangular load like this, right? So you have to consider the entire triangular load like this, right? So this entire triangular one. So now you know, now because like you are coming to a distance that is little bit before 18, that means definitely it has passed this point, because guys this point is 16, because up to here it is 16 and up to here it is 18. That means definitely you have to pass this section, right? So definitely you have to pass the section. So you have to consider this one. So then you have to evaluate the total load. So total load, what is total load? Total load is the area. What is the area? Half into this base. What is this base? What is this base? Half into base means 10. Half into base is 10, and this height, this 120. So that is what they have done, half 10 into height. So the next thing is the distance. So how to get the distance? So that is the next part. So that means that distance means here you need to evaluate the center of gravity. Okay, because now if you are going to consider this triangle, guy, center of gravity is 1/3 of the length, 1/3 of this horizontal length from the height side. So now as you know, this is the height side, so the center of gravity is here. So now you need to find the distance from here to here. Is that so? It's very easy, right? So you need to find this distance. So that's very easy, it's not hard. So how to evaluate that? Because we know this distance. What is this distance? What is this guy? That is simply this distance is 10 divided by 3 into 2, because 2/3 of that, because this distance is 2/3 of 10, so 2/3 of 10, and you have to add this portion plus 6, right? this distance plus this distance, and the total amount just deduct from x. I think that is the scenario. So see, that is what they have actually done there. See guys, x minus 6 minus 2/3 of 10, x 6 2/3 of 10. So that's it. So that's it. So that is it. That is how you should get it. So that's the way to get it. So now you can get the general equation like this. And be very careful guys, you have to very carefully do the simplification. So now this is the general equation. So 992x minus 1020 into x minus 8, something like this. So now put the limit guys. Now what's the limit? So according to this case, it should be definitely, this x should be definitely greater or equal to 16, right? You should know that this limit definitely should be greater or equal to 16 and less than 18. That's the limit. So put the limit, one limit at here and the other limit at there. So I think now you can understand how to get the bending moment value. So that, and the same scenario you can do for the shear force. That's nothing new guys, that is just about considering the forces. So now in considering the forces, as you can see there, okay, let me just undo that. Let me just undo everything. Okay, right. So you know, when you are going to consider the shear force diagram, what are the things that what are the forces that you are getting within this section? You are getting this reaction force and this rectangular load, the resultant of the rectangular load and the resultant of this triangular load. That's it. Because you are not getting this one. Why? Because you have not yet passed this, because you are at here, you are at here, not at here. So those three are the only types of forces that are coming. So that's it. That's it. Right, so that's it. So 992, 1280 and 600. I think this is for the triangular guy, this is for the total rectangular guy, and this is that reaction. That's it. And here it's so little bit special because if you're going to consider this this shear force equation, that shear force for this section, right? So in consideration of shear force for that section, there is no x term coming in this section up to there. In this section there is no x term coming. That means the general equation has no x terms. Okay, so that's the little speciality. Okay, that's it. So the next target is to move on to the last section, the section DE. I think I will not give you the answer for that. Now you can do the section DE on your own. Doesn't matter, I can help to check the answer. Okay, so I will give some time for you to get the sectional equation for the section DE. Okay, so now we are moving on to the last part, right? So the last section is the section from 18 to 20. So now we will just see why that section is considered as a separate chapter. Like, what is the reason for considering it as a separate section? So now, as you know, this is our diagram. Okay, so I have previously explained you, we are going to make certain sections. So like that, now we have reached up to the last section. So from A to B there is a section like this, and then we continued section B to C, then C to D, and then the last section, section D to E. D and E, the last section. So the reason why we are going to consider it as a separate section is because of this reaction RE, right? So that is why we consider like that. I think now I don't need to give complex explanations, because now you know everything, because previous sections I explained in detail from A to Z. right? So now, but the only thing is, like, when you are going further and further, like when you are going to move this now, see guys, now earlier our H section is only up to here, I think you can remember. Then our X section continued up to here, and then our X section continued somewhere up to there. So now our ultimate X section is going to continue up to here. Now up to here means I already told you that when you are going to do the sectioning, you are just going to break it like this, some little distance, some very little distance, I mean this distance delta x away from the end, right? Because now at the end we are getting a new member which is RE, the reaction force. So that is the reason, right? So now we can consider each and every force, right, that is responsible for the shear force diagram, and then each and every moment, right, that is responsible for the moment which is applied through the section. I think I will sketch the section. So now this is our section, right? Okay, that means we are going to break the beam at here, right, some little distance away from the end. So the x distance, I can say it is the x distance measured from this extreme left end up to this section. Yeah, so now you know it's very easy. We have positive shear here, right, because left side is going up. Then this rectangular thing, and then we have this triangular one. And now look here, this 40 kilonewtons, right, this 40 kilonewton, because now the reason earlier we didn't get this 40 kilonewton one, right, because now the earlier, according to the earlier limit, this 40 kilonewton thing is not applying actually. Okay, because now our limit is x greater equals 18, because now up to here, because now up to here we have 18. Okay, and our next limit is x greater or equals 18 and less than 20. So now this is our limit. So now we know what are the forces that contribute to the shear force: this reaction, rectangular load, triangular load, and this downward vertical load. And this is also negative shear. Why? Because of this the left side will go down. Okay, so now go to the equation. I think it's very easy. RA, that's the reaction, very easy. The triangle, I think I will for your betterment, I think I will highlight that and show you, so you can get a much clear idea. Okay, so now you know this RA part, that's okay, the reaction, that is positive. And then this is because of that rectangular load, the rectangular load, this part. And this is from the triangular load, this part. And this is the vertical load. Now see, direction negative for the vertical load because negative shear, direction negative for the triangular load because negative shear, and also direction negative. And from here also, see, now look here also, if you are going to consider the shear force diagram, not the diagram, the shear force equation, the general equation for the shear force for the section DE, right, it's a just fixed line, it is a fixed number, minus 928, right, because there is no any sort of x term here, right, so there are no variables in the shear force equation, right. I think it's easy, right, it's very easy. So now we have the last part, which is the bending moment guy, right. So in order for you to understand these basics, I took this much of effort. I think now you can very easily, even you can very easily find this. I think now the shear force is okay. Okay, so now quickly let's see whether we can understand the bending moment guy. Okay, I think I need the diagram again. Okay, so doesn't matter, I will again go for the diagram again, copy of the diagram again. right. Okay, so that's right. Right. So now here, because of this reaction, because of this reaction, uh, the bending moment is, what would be the direction? So it is positive, right? So it's positive. Why? Because left side is going up. Okay, so positive bending moment. And because of this guy, again it's no doubt, it's the left side going down, that means it is negative. And because of this guy also, because of the center of gravity at here, this also causes negative bending moment. And what about here? Because of this guy also causes negative bending moment. Why, guys? Because left side going down, left side going down, so negative, left side going down, so negative, left side going down, so negative. This is the only force that causes left side to go up, so it is positive. So now we have to worry about the distances. So now you know this is the place we are going to break, and this is the distance x. What can you say about the distance for this reaction RA? That is x. See this distance, right? I think RA is okay. This RA multiplied by x. So very clear. And 1280, this is because of the triangular load. It is negative. And why x minus 8? So let's see why it is x minus 8. Because now we know the center of gravity to the rectangular load measured from the left end is 8. Right? From this left end to the center of gravity of the rectangular load, it is 8. So the distance from the center of gravity of the rectangular load to the section where we are going to consider the moment, so that is this distance x minus this distance will give the distance from here to there, which is x minus 8. Is that clear? Okay. And now here, so this is also easy. So we know the distance from this non-height side to the center of gravity, which is 2/3 of 10, right? Which is 2/3 of 10, because 10 is this base length, and this length we know it is 6. So the total length up to this, the total length from this left end to here is 6 plus 2/3 of 10, right? So then in order to find the distance from here to there, because we need this distance, so what is that? So it would be x minus in brackets 6 plus 2/3 of 10. 2/3 of 10. This is 2. Okay, so that's it. And the last one here, there the vertical load that is acting downwards. So what would be the distance? Because the distance from the left end, because this is the left end, the distance from the left end to here. So what is that? 6, 10 and 18. The distance to the vertical load from the left end is 18. So what would be this distance? That is x minus 18, right? So that's the scenario. See, I think this is also now what is this half into 10 into 120? That is the area of the triangle, right? X minus 6 minus 2/3 of 3, that is the distance. And see, this is x minus 18 is the perpendicular distance from this vertical load to the point where, or the section where we are going to consider the moment. So this is the equation, right? So now the fact is, like, when you're going to solve these equations, you can't say, like, it would be really pointless even after a lot of calculations if you are obtaining the wrong one, so you are not awarded any sort of a mark, because it is wrong. So the next thing is, guys, carefully you have to solve this. So after solving that, you would be getting a general equation like this. So what is this? This is the general equation G dot E, general equation for the last section DE, which is defined by x greater or equals 18 less than 20. So after solving this, just put the limits. So what are the limit values? First put x equals 18, get this value, then put the last one x equals 20, then get this value, and also be very careful about the units. So that's all about the analyzation of the formula for the shear force and the bending moment for the last section DE, which is defined by x greater or equals 18 less than 20. So that's done. Okay, so now we will focus in order to sketch the shear force and bending moment diagram. So now I will explain you everything step by step, logically, how to sketch this shear force and the bending moment diagram. Guys, this is completely a science, right? So this is completely a very logical thing. So now let's see how to do that. So now we will first focus to sketch the shear force diagram. So now we know that previously we just separated this beam into certain sections. I think you know that, like section AB, okay, and then the section BZ, and then CDE and DE. So like that we separated. Okay, so now we are going to sketch the shear force variation, or the representation of the variation of the shear force at those particular sections, right? So this is completely a very logical thing. You cannot just sketch it, so be very careful. Okay, so now let me concentrate on the calculation that you did previously. So now this is our very first calculation. I think you can remember, the first consideration is consider the section AB, right? So as you know, we did calculations for that. So now you know, now I do not need to teach you how these equations are formed and how we calculated these things. You know everything now. So now just focus the general equation for this. Okay, so guys, what is this general equation? So this is simply like, you know, that y equals mx plus c type, right? So very easy. And now you know the shear force at two particular limits, because guys, you just define the first section. This is the first section, right? So you define this section where x is greater or equal 0 and less than 6. So that is how you define that, and you found two values, x when x equals 0 this much, and when x equals 6 this much. So you know those values. So now the first thing is, guys, so that means at this section. So now actually, you know, this line, right, this axis represents x, that means that length. Okay, so that represents the length. So so then when x is 0, x0 at here, you know the value of shear force, it is 992 at here. And then when x equals 6, when x equals 6, what is the shear force? 512. X equals 0 this much, and when x equals 6, it's 512. So just mark this, x equals 0 this much, and when x equals 6 this much, right? So now this value is corresponding to this section, this location, and this value is corresponding to this location. So now the next thing is, you just need to connect these two, just connect it, right? So now guys, just see carefully, this connection is a straight line, right? This connection is a straight line. Why? What is the reason? Because the reason is the connection between these two ends, right? The connection between these two ends is actually given by the general equation, because the general equation is a straight line. See, y equals, actually it is y equals minus mx plus c. So whatever, the general equation is a straight line. So we are going to connect these 2 points by a straight line. Why? The general equation follows the equation of a straight line. So that is simply as that. It's a straight line. Now you know that. Okay, so now let's move on to the next section. So what is the next section? Next section is between 6 to 16, I think, right? Because why, guys? Because in this particular case, you can remember x is greater than 6 and it is x is greater than equals 6 and it is less than 16. Okay, I mean this section. Right, now we are focusing this part, right, this part. So that means here x greater here and less than here, right? So now how to sketch for that? Now see, this is that can I use a different color? Okay, line color, no, it's okay. Right, so now according to this section, again, now still I am going to consider the shear force diagram. Okay, so then go to the calculation of shear force in the next section. So it is this. So this is the general equation. This is the general equation of the shear force for the next section, which is defined by greater than 6 and less than 16, as here. Okay, so now look here, what are the two values that you found when x equals 6, 512, when x equals 16, minus 888. So the number one thing that you need to do is first mark that when x equals 6, the value is this. Actually the first value, I mean the first point of the next section and the previous value of the last section are actually coinciding. Okay, so first mark for the next section, mark the first value according to the first limit, x equals 6. It's clear. And then what is the next value? When x equals 16, what is that value? Minus 888, which is here. See, this is minus 888. That's it. So now the next target is how you are going to connect that. That is the next target. Target is how you are going to connect that. This is one point and this is the other point. This is the value of 512, right? So this is 512. Oh, just I will just erase that. I think they need to, it would be clear. Okay, okay, right. So now this is 512, right? And this is minus 888. So now the next target is how you are going to connect this. So can you connect this by a straight line? Can you connect by a straight line? No, definitely wrong. Guys, why you cannot connect by a straight line? See, the reason is the general equation. So look at the general equation. So the general equation is not a straight line, it's a quadratic, right? So it's a quadratic, so no problem. So now we know the general equation is a quadratic thing. So that means we can either connect it by this or we can either connect it by this. Okay, so now considering the shape of the curve that we are going to connect the next section, the section which is x greater or equals 6 and less than 16, I mean this particular section, right? Because we know when x equals 6 it is 512 the shear force, and when x equals 16 it is minus 888. So we know that. So now the doubt is how we are going to connect these 2 points. Okay, so so now basically when connecting these 2 points there are 2 possibilities, as I told you. So the first possibility is we can sketch the curve like this. I mean, like this is the particular point and this is that point. Okay, so first we can connect like this, right? So we can call this type as type 1 curve. Okay, now because now basically there are two types of possibilities how you can connect, and we should argue for that, we should justify that why we are getting such a kind of a curve. Okay, so the next possibility is we can sketch a curve like this, right? So either type 1 or either type 2, right? So now let's just analyze what sort of a curve that should actually come, or like what sort of a curve that we should consider. So so now let me just consider the type 1 curve. I told you type 1 curve is like this, right? So this is 512, this is minus 888, so no doubt in that. So now when you are going to consider this curve, let me just sketch something like this. Okay, so now just sketch some tangents like this, some random tangents like this, right? Some tangents, right? So now just sketch some tangents by considering those tangents as the hypotenuse of the triangle. Now just consider right angle triangle, right? So if you're going to consider this triangle, this is the right angle and this is the hypotenuse, you know that. So now just sketch this kind of right angle triangles by considering this tangent as the hypotenuse. Okay, something like that. Okay, something like this. Okay, so now in this case there is something that you can notify. So when you are going to consider this curve, and if you are sketching some tangents like this, right, by considering the tangent as the hypotenuse of the triangle, and if you focus on this height, this height, this height, this height, and this height, and if you are just going to focus on the height, you can see the height is increasing. I mean, like, say this height is height 1, h1, and say this height is height 2. I'll use a bit dark color. Say this height is height 3. Okay, say this height is height 4, and you can see the height is increasing. Okay, okay, so for your betterment I will explain the same thing again, so no doubt, right? So no worries, I will explain the same thing again for the betterment, because now previously also I explained, and previously you have a kind of an idea. So now when I'm going to explain that for the second time also, you can have even a better idea. Okay, okay, let me just sketch it again, right? Okay, no doubt, right? So now this is the curve that I sketched. I think that is clear. Okay, so this is the type 1 curve, this curve, and this point is corresponding to 512, and this point is corresponding to minus 888. So now just randomly sketch some tangents. Carefully sketch the tangent, otherwise you will get the wrong idea. And it's bit difficult actually. Okay, doesn't matter. So just consider these tangents: tangent 1, tangent 2, and tangent 3, something like this. Okay, So now when considering these tangents, now you can complete the respective triangle for that. Is it clear? Right, so this is triangle 1, okay, this is triangle A, this is triangle B, and this is triangle C. All okay. So now in these triangles, just consider this height, this height, this height, and this height, and you can see the heights are increasing. This height is greater than this one, and this height is greater than that one. So if this is h1 and if this is h2, if this height is h3, you can say h3 greater h2 greater h1, right? Is that clear? So because of that, for this kind, I mean like for type 1 curve, for a curve like type 1, we call this is an increasing curve. What type of curve? Increasing curve. Increasing. I think now you got the point, right? You are just sketching some like tangents, right? You are just sketching some tangents, and then what is the next thing? You are going to consider these tangents as the hypotenuse of the triangle, and you are going to complete the triangle, right? So if you are going to consider the height of these triangles, you can see the height is increasing. So for this type of a curve, you call it's an increasing curve. Guys, why it is increasing type? Why it is increasing type? Guys, the reason is why it is increasing type is that the reason, see, the load intensity is increasing, right? Because when it is moving from here to there, you can see the load intensity is increasing, right? See, this more than, like, this line is greater than this one, this line is greater than that one. So here you can see very clearly the intensity of the load is increasing, right? So it's increasing, right? This length is higher than that previous one, and this length is higher than that, like that, because it is a trapezoidal load format. So the load is increasing, right? It's increasing. Why? Because the load intensity increasing. I hope now you can understand that basic scenario, okay? And also I think now you can analyze the second curve on your own without any sort of doubt. Okay, let's just check whether you can analyze type 2. Okay, first analyze type 2 like this, in a separate place like this. Okay, so this is, I told you this is type 2. Okay, now just say this is type 2. You don't need to sketch the tangent, okay, doesn't matter, just consider the curve as a triangle. Okay, no problem, just consider like that. Okay, so I will select a different color. Okay. Okay, now just consider like that, this one, but I think it's better to consider it with the tangent, because otherwise you can purposely increase or reduce these heights, so in that case it will not be fair. Okay, doesn't matter. So now I will sketch certain tangents. Okay, okay, I think that tangent is not good. Okay, that tangent also not good. This is a manual working, guys. I'm trying my best to understand this to you clearly. That's a tangent. Okay guys, so now consider, okay, so now just consider, okay, now complete this triangle. Okay, it's a little bit difficult. Yeah, now see, so now you can consider, so look at this height, so let's call that okay, say capital L1, and look at this height, capital L2, look at this height capital L3, and look at this height capital L4, look at this height capital L5, and you can approximately see that the lengths are actually decreasing. That means L1 is greater than L2, and that is greater than L3. That means the height of these triangles, like if you are going to consider this as the triangle, right? So this is the height, this guy, right? So you can now very clearly notify the height is decreasing. So that means this is decreasing type curve, right? So I think now you got the point, right? So now we got the point. So that is why when you're going to consider this bending moment diagram, not bending moment, is actually shear force. Now this is that curve. Sometimes now this is that curve, guys. Now see, this is a curve actually. See, this is a curve. This is the original sketch, right? So actually this is a hand sketched one, right? No any software. So now actually guys, this is the, see, I have mentioned second degree curve. See, second degree curve, guys. Why it is second degree curve? Because just look at the equation. Look at the equation for the next section. If you're going to consider the equation C, it's a second degree curve because it's a quadratic, right? So that is how this curve came, right? So that is how this curve came. So this is increase in type, right? See, that's increase in type. So that's how it came. I think now that shear force diagram part is now clear. So now let me consider the remaining calculation. And now AB okay, BC okay. Okay, now consider CD. So nothing much to worry in CD because it's a fixed line. Why? When whether x equals 16 or whether x equals 18, doesn't matter, it is minus 888. Nothing much to worry, right? It's just, it continuously minus 888. No worries. See, it's minus 888, right? It's minus 888 like this. Okay, it's minus 888. And then focus the last point, which is DE. DE also it's the same scenario. Whether x equals 18 or 20, the shear force is minus 928. C is minus 928. This is minus 928 line. See, it is also something like that. But you have to continue. Be very careful when you are going to continue the line. So be very careful when you are going to continue the line. So this is the representation of minus 888, okay, and this is the representation of minus 928. But when you are going to connect, you should connect like this, right? So that's the case. So this is a straight line because why? The reason y equals mx plus c format, and this is a second degree curve because why? The reason is the equation that represents the shear force, the general equation for the shear force that represents section BC is a quadratic. And then we have a doubt whether it is increase in type or decrease in type. Actually it's an increase in type, guys. The reason is the load is increasing because we have that trapezoidal load format, right? Because we have the trapezoidal load format. So I think this part also clear, and the next two remaining sections you are getting a constant value, and this is how you connect that. I think the shear force diagram analysis is now very much clear, right? So now that's the shear force diagram representation. I think is there any sort of a clear way to get that? Yeah, right. I think it's clear, right? So this is all about the shear force diagram. Okay, so if it is not clear, now you can again take a look into the shear force diagram. I can just I will just delete these members. I will just delete the things that I have sketched, then you can have a good idea. The analyzation for the shear force is now perfectly fine, isn't it? Right, so you know everything now. Okay, I will reduce a little bit. Okay, right, so now you know how this part comes, how A to B comes, you know how B to C comes, you know how C to D comes, you know, and how d to e comes. Now you know that very logically. So I think everything is clear now. The shear force diagram is clear. Okay, so now we will focus how the bending moment diagram comes, the next guy. Okay, so now we will be discussing how to sketch the bending moment diagram. So now this is very much closer to the end of the session. So now we have successfully sketched the shear force diagram. Okay, right. There are certain things like certain steps that I need to teach you. Okay, let's see. So now again go back to your calculations, right? So now here focus on the general equation for the bending moment according to the first section. So now you know our first section is AB. So now focus the general equation for that, right? So now you know when x equals 0 the bending moment is 0. When x equals 6 the bending moment is this much. You know that. So then you know this is the respected section. So just go down and locate this is the bending moment diagram, right? This axis represents the bending moment, and this is the distance. This is actually the x-axis. Okay, so now when x equals 0 the bending moment is 0, no problem. When x equals 6 the bending moment is 4512, right? Now I think that is clear. According to first limit, the bending moment value at x equals 0 is 0, and when x equals 6 the bending moment value is 4512 as according to your calculations. So now our next target is how to sketch this. So now I told you need to connect these 2 points. So that connection follows the general equation as described according to the format of the particular equation. So sometimes that equation can be first order, I mean like y equals mx plus c type, then second order, third order, fourth order, so on. So now then when you are going to connect these 2 points, now you need to worry about the general equation. So I will use a different color. So now look at this general equation. See, this is the general equation. Okay, so this is a second order equation. Why? Because x to the power 2 is there, so this is a second order equation, right? So it cannot be a straight line. So this is a second order equation, right? So now I will go back to my sheet, right? So we know that one value is 0 and the other value is 4512, right? So this is the bending moment axis and this is the distance axis. Okay, so now you know these 2 points, one is at here and the other one is at there. Okay, so let's say like that. Okay, and this distance is say 6, right? This is 0 and this is 6. So now when you are going to connect, there are 2 possible ways, because like this thing I already explained you in the shear force part also, right? There are 2 types of possibilities. One, you can connect like this, okay. The other way you can connect like this. This is, let's say, type 1 and say this is type 2. Okay, so now there is a certain thing that I need to teach you. So now you just consider type A. Okay, just consider type A, right? So what is type A? Okay, type A is something like this. Okay, let me sketch like that. So be very careful about the slope, like you can't get too much slopes like this. Okay, so just sketch a general slope like this. Okay, so don't go for too much of curving right, because actually this is a sketch, because you are not using any simulation softwares. Okay, so just sketch a normal one like this. Okay, so now let me teach you this thumb rule or this little principle. So now you can sketch certain tangents, right? So you can sketch some tangents, right? Okay, so you just can sketch tangents like this, and like this, right? You can just sketch tangents. So but be very careful when you are going to sketch these tangents. Sketch the tangents of equal length, understand? So when you are going to sketch the tangent, sketch the tangents of equal length, like the same length, right? This length, like consider the same length, right? So after that, then considering this tangent as the hypotenuse of the triangle, you can simply complete the triangle, right? You can very simply complete the triangle. Okay, so now I want you to focus one thing. Okay guys, right? So now if you are going to consider these triangles that are formed, again I want you to concentrate uh, on this length. It's not length, so let's say that height. So this height h1 and this height h2 and this height h3 and this height, so let's say that h4, right? So here you can very clearly observe that height h1 is greater than h2 and that is greater than h3. That means when we are moving towards the x-axis, the height is reducing. Okay, and I also told you actually this height is corresponding to the slope. Okay, the height is corresponding to the slope. So when the slope is increasing, the height is increasing. So when the slope is decreasing, the height is decreasing. Okay, so I think now that is clear. Okay, so now be very careful about this part. It's a very serious thing. So now also when the bending moment is maximum, like the bending moment is going on increasing like that, or maybe decreasing, whatever. So as according to our simple basics, that at the point where it is maximum, like if you consider any like maximum position, say if it is maximum, what can you say about the slope? Dm by dx, I mean like at the maximum point the deviation is 0. I think that is simple basics. Actually the slope or the derivative of bending moment, right? The derivative of bending moment at a particular x point is same as the intensity of the shear force at that particular point, right? So the the deviation, I mean dm by dx, the first derivative of the bending moment with respect to the distance, dm by dx equals to the intensity or the shear force at the particular section. Okay, so that is the basics. So now here consider according to this diagram, right? So according to this diagram, the thing that you can notify, what can you say about the intensity of the shear force? The intensity of the shear force is reducing, right? See, very simple basics. The intensity of the shear force reducing, because it is reducing from 992 to 512. So this shear force is reducing. So if shear force is reducing, then what should happen to the dm by dx? Because I told you dm by dx is same as the intensity of the shear force, right? So if this guy is reducing, this guy should also reduce. Okay, and here I told you there are two possibilities, possibility type 1 and possibility type 2, and we already analyzed the possibility type 1, this guy, this curve. So what happened in this curve? When x is moving on, the slope is reducing. See, this is higher than this one, and this h2 higher than it. That means you can see very clearly the slope reducing, right, according to here. So slope reducing means, what is the meaning? Shear force intensity also reducing. Understand? So what is the suitable curve to that point? It should be this curve. Why, guys? Because the reason shear force intensity reducing, that means the slope is reducing. Because if you are going to consider this curve, the curve type number 1, the slope is reducing. Why slope is reducing? Because that reducing of the slope is corresponding to the reduction or the reducing of the shear force intensity. Because now when you are going to analyze the bending moment variation, what is the primary data for that? So in order to sketch this, you need to have a primary data. So what is the primary data? Primary data is this. So this is reducing, the shear force intensity reducing. That means the bending moment variation according to that, like this slope according to the shear force should also reduce, because you can't have because you can't have increase in slope for decrease in the shear force intensity. Because if the shear force intensity is reducing, you cannot have slope of the bending moment diagram increasing. So if shear force intensity going down, so the bending moment slope, the slope of the bending moment diagram also should go down. So that means the only possible curve is this one. So that is why we have sketched it like this. Actually this is appearing like a straight line. Okay, but this is not a straight line. So this is type 1, curve, something like this. Okay, because it's very difficult to symbolize over there. This is a type 1 curve, right? This is a curve actually. I think very difficult to sketch it, right? So here what we have, okay, let's sketch like this. Okay, so here what we have is actually type 1 curve, something like this. Okay, so now I hope that is clear. Okay, but so now sometimes you might be wondering, why should we need to believe type 1 curve is the best without analyzing type 2 curve? Okay, doesn't matter. So I will analyze type 2 curve also, right? Okay, right. So now I will analyze type 2 curve for you. Okay, so guys, now what is our type 2 curve? Again, if this is our axis, and this is 0, and this is what is that value, 4512, right? Is that so? Yeah. So now I am going to analyze what would happen if it is type 2. So this is type 2, okay, because now I am going to analyze for type 2. Okay, so now what is the theory? Theory is just generate some tangents of the same length, right? Generate tangents of the same length, right? Because you can't have tangents having different lengths. That means you are purposely cheating according to your desire. So don't do like that. Generate tangents of the same length. Oh guys, there is another way. Okay, now here what you are going to do, you are going to generate tangents of the same length, right? So like that you are going to generate tangents, you are going to generate some tangents, right? So now rather than generating tangents, right guys, there is another trick. I don't mind for that. Rather than generating tangents, you can directly consider this arc as the tangent. Did you get that? Rather than generating the tangent like that, you can directly consider this arc length as the tangent, okay, something like this. So if you are going to do like that, then select the same tangent length like this. Select the same tangent length somewhere at there. Select the same tangent length, then at here, somewhere like here. Okay, so now guys, according to this case, now you can approximately see what can you say about this height, what can you say about this height, what can you say about this height, what can you say about this height. So if you think that I am purposely sketching this for my desires, you can sketch it. What can you say about this height guys? So this height is increasing, so this height increasing, right? So this height increasing, that means slope is increasing, right? And I told you dm by dx, the derivative of the bending moment, is actually corresponding with the shear force. So if the slope increasing, then dm by dx increasing, so that means shear force intensity should increase. So you cannot have that. Why? Because according to here, the shear force intensity is dropping down, so you cannot have type 2, so you cannot have this type. So the same way you can analyze for here. See guys, now see guys, this height is increasing, this is higher. So if I say this is alpha 1, if I say this is alpha 1, this height is alpha 2, this height is alpha 3, so you can see alpha 2 greater than alpha 1, then alpha 3 greater than alpha 2. I think because of that, type 2 curve is not suitable for that, okay. So the most suitable type is the type 1 curve. So according to the real case, this appears like a straight line. Guys, actually it's not like that. This is a second degree curve of type 1, okay, right. So I think now we analyze for that. So now the next case, is now you should now I told you there is a simple basic, there is a fundamental thing, right? You know, there is a little fundamental thing that dm by, because I previously also I told that, you know, dm by dx, the first derivative of the bending moment corresponding to the length, symbolizes the intensity of the shear force at the particular location, okay. So you know, that means if the bending moment is maximum, right? So say for an example, at this point the bending moment is maximum, right? Say this is the maximum point, say this is the maximum point. So at here, if the bending moment is maximum at here, so what can you say about the slope? At this particular slope, dm by dx should be 0. dm by dx should be 0, right? Okay, so now by looking at this curve, you know, at one particular point dm by dx should be 0, right? At one particular point dm by dx should be 0. Why? Because at that point bending moment is maximum. Did you get that? Okay, I think I will explain that little part here again, right? So if you are going to consider the bending moment curve, at one particular point you will be getting the bending moment as maximum. So if it is maximum, what should happen? dm by dx should be 0. So if dm by dx is 0, what should be the shear force intensity? That also should be 0, because these two are directly related. So that means if the bending moment at when the maximum position of the bending moment is reached, the maximum position, when the maximum position of the bending moment is reached at here, at the same corresponding point, the shear force should be 0. Now see, this is 0, this is shear force axis, so shear force should be 0. So now you need to locate what should be the possible region where you can have 0 shear force. I will again tell what should be the possible region where you can have 0 shear force. Is that clear? So you cannot have 0 shear force here, you cannot have 0 shear force here, so you cannot have it at there. So only possible region is this region. So only possible region is that. So when you are going to sketch the maximum bending moment point, right? So when you are going to sketch the maximum point, you should sketch it parallelly as corresponding to the point, because you have to match the point, you have to match the maximum bending moment occurring point with the 0 shear force point as according to here, right? Because this curve this second degree curve we already sketched previously. Okay, so now I hope that is clear. So now what is the next section? The next section is section B to C. That means this guy, right? That means this guy, right? So before sketching that guy, okay, I will just undo that. Okay, I will just undo that, right? Okay, I will just right. Okay, so now before sketching this guy, before sketching the section, like before analyzing section BZ, so let me go to the general equation for the bending moment of the section BC. So now where is our section BC? Yeah, it's here, right? So now this is the general equation for the section BC. Okay, this is the general equation for the section BC. So now you can very clearly see, guys, it's a third order equation. What order? It is third order, right? And not only third order, you have to match the maximum bending moment occurring point with the 0 shear force point, because when the bending moment is maximum, it will give you the 0 dm by dx. So at the same point it should match with the 0 shear force occurring point. Understand? Done. So that means, guys, simply I'm telling you one thing, that means you need to find what is the value of maximum bending moment. See, you can see here the slope is 0, is a horizontal line, right? So that means you need to evaluate what is the maximum bending moment. Okay, so it's very interesting. So let's calculate that. Right, so let's calculate that. Okay. right? So now I hope the sheet is clear with you, right? Evaluating the position where maximum bending moment occurs. So this is very important. So when maximum bending moment occurs, we know dm by dx equals 0. When maximum bending moment occurs, dm by dx equals 0. That means the shear force intensity SF should also be 0. So that means, what is this guy? Now, because guys, in this problem there are so many sections, right? Section from A to B, section from B to C, right? So why we considered only this general equation? Because guys, first thing is you need to find logically what is the possible region where you can have the maximum bending moment. Understand guys, I don't need to show you the diagram. You should logically think what should be the possible region where you can have the maximum bending moment. So it is the region B to C. So that means you have to consider the general equation for the bending moment of region B to C. So this is the general equation for the bending moment of region B to C, because that is the only possible region. That is the only possible region where you can have maximum bending moment. So this is the general equation. So differentiate that with respect to x once. 992x minus 40x squared minus 2 times x minus 6 to the power 3. So if you are going to differentiate that, it is 992 minus 40 into 2 into x minus then 2 into 3 into x minus 6 to the power 2. That's it. So now this is the derivative, and this equation also represents the corresponding shear force equation for that. When the bending moment is maximum, dm by dx equals 0, and this is dm by dx, so that means this guy should equal to 0. So that means just solve this. You would be getting a quadratic, so you can use the calculator or whatever. So there are two possible answers, x equals this much and x equals that much, so you can't have minus value. So the only accepted value is x equals 10.72. X equals 10. Then what is the meaning of that? When the length is 10.725 meters measured from the extreme left end, that would give the position where the maximum bending moment occurs. So you know the corresponding length where the maximum bending moment occurs, so put that value x in the bending moment equation. So put this value in the bending moment equation, so you can find the maximum bending moment. Simply as that, right? So that means guys, just move that much. That means what is this length? So this length is that 10.7, I think, what was that value? I don't remember that. I think it is how much? Yeah, 10.725. yeah. So guys, what is this length? It is 10.725, right? So that is this length. This is the length where the maximum bending moment occurs. That means shear force 0. See guys, see, this is the point. Okay, so that is the point. So I hope that is clear. Okay, so now we need to analyze the other two remaining sections. Okay, so let's quickly analyze that. So that means the entire problem is over, right? I think now you have a very basic idea from A to Z on how to do this. Okay, so now the last two analyzations. Okay, so now I need to go for the general equation for the section ZD. Okay, so now let me consider section CD. Okay, section ZD. Go for the general equation. I think this is the general equation. Guys, what can you say about the general equation? So this is the general equation for the section CD. X, X, X. So this is a first order one, right? This is a first order. That means y equals mx plus z type, right? So very easy. So it's a straight line. So that means you know there are two values when x equals 16, when x equals 18, because those two are the limits. 3632 and 1856. See, because you need to locate the values. So this is the value corresponding to x equals 16, I think, right? And this is the value corresponding to x equals 18. So here it is 3632, sorry, 3632, right? So okay, so you can match it like this. So this is 3632 and this is 1856. So the only possible way to connect is by a straight line. Done. And the next case, the final part, the last section DE, again go to the bending moment equation. So look at the equation type, look at the type of the general equation, x, yeah, it's the first order equation. It's the first order equation, that means a straight line. And you know the corresponding bending moment values at the corresponding limits. When x equals 18 this much, x equals 20, 0. Yeah, so when x equals 18 this much, when x equals 20 it is 0. So only possible way to connect is by a straight line, right? Straight line, see, it's like that. Okay, so that's it. So our mission completed. So this is first order, this is a first order curve. I'm like, because now the reason why I'm telling like this is that don't just sketch whatever the diagram, because you don't have any idea before sketching. So don't do like that, because guys, this is engineering. You should have an idea about what sort of a curve that you are sketching. First order, I think this is third order. I think it is third order, right? So let me check the section BC. Yeah, section BC is third order. Yeah, so I think it is done. And this is I think second order. Yeah, it's second order, I think. So that's it. So guys, I think now you have a very clear idea about the bending moment type questions. I mean, not all the type of questions. So simply this is the question that we analyzed, right? This is the type of the question that we analyze. Now you can again go back to the first session, how I analyze this. So don't all the time, do not expect for you to give the diagram like this. So you need to understand the loading structure and everything. So I expect to do more questions, to analyze more questions. And the most important thing is that don't expect me to do the lectures in 15 or 20 minutes, because you will never understand that, because those lectures are good for somewhat brilliant students. I don't have to deal with brilliant students. I am teaching with students who have a very poor idea on this. Okay, so that's it. So now I explain A to Z. Now anybody can sketch a bending moment diagram. If someone listens to this video, anybody can sketch bending moment diagram like this. Okay guys, so wishing you all the very best for your exam. So I wish to meet you up again with other type of bending moment questions. Okay guys, thank you so very much for your valuable time. Thank you. God bless.